This is ECE 3400 Analog Electronics, Project 2, Spring 2014. I'm Stanley Lewis, and I'm here with John Garrett. We're doing a Mosfet transistor circuits report. Here's the common source questions. We're comparing our non-ideal gain to our ideal gain. Solving for our non-ideal gain, we use kappa n from our previous project, which is 0.707, to solve for a gain non-ideal, which is half of the ideal gain of 552.34. As you can see, we are answering most of the questions about the gain and how does it change with bias current. It increases and decreases proportionally. We would increase the transistor width and decrease the length in order to increase the IREF, which when we do that, we use that to increase the gain. Here is a comparison of our PFET common source amplifier. On the left is measured data and on the right is simulation. As you can see, with our previous data from our previous project, we used to make a graph to get a gain very similar to the measured data. The gain is equal to the slope. Differential amplifiers. We assume that all MOSFETs are in subthreshold region if the bias current IB is in the subthreshold region itself, because IB is the combination of the two output currents, I1 and I2. These are the equations that we use to solve for our I1 and I2. When V1 is a lot smaller than V2, I1 is shown as I bias over 1 plus e to the kappa of V2 minus V1 over U of T.
These are the graphs for the differential amplifier currents. This shows input voltage versus output current. On the left is the measured data, and on the right is the simulation data. These graphs show I1, I2, I1 plus I2, and I1 minus I2. You can see the data is very similar. We then graph them on a log scale. Again, on the left is the measured and on the right is the simulated. For the measured, we had slopes of 28 and negative 28.9, and for ours we had about 22.7 and negative 22.7. This is a curve fit for I1. We used a curve fit using the equation in the middle to find a value for I bias and kappa over U of T for each of the equations. This is our curve fit for I2. We again used a revised equation in the middle to curve fit for an I bias and kappa over UT for each. These are our curve fits for I1 minus I2. We used a Tanch equation to curve fit and find an I bias and kappa over UT. Overall, for the three, our I bias and kappa over UT did not change very much between the three graphs, while for the measured data it changed slightly between all three. Here is a curve of the input voltage versus the output current for the transconductance amplifier. We used a curve fit to find and solve for a value of I0 for each. This I0 value could be caused by the current mirror supplying more current than usual, than desired. MOSFET 1 has a higher turn-on voltage than MOSFET 2. I0 seems to barely change with the output voltage, and raising the bias voltage raises I out.
Here are the two graphs of measured data and simulation data that we're using to find our gain of the circuit. As you can see, we use the slope of the line from the input voltage compared to the output voltage to find the slope, which is the gain. Our measured data happens to be 1/3 of the gain of our simulation of data. We use the slope of a line compared output current to output voltage, and 1 over the R out equals the slope of these lines. So we found R out by finding the slope with the curve fit, as you can see, our simulation data. And we came out to two very similar answers. We found GM by taking the negative slope of the output current versus the input voltage of the simulation data of the transconducting amplifier. The two transconductants are very competitive. Here is a summary of the values we solved for using our transconducting amplifier. As you can see, our R out, GM are very similar to the measured data. Also, our gain has calculated to be exponentially larger than our measured data gain. Also, we have an error that is unproportional to the correct error or a similar error that comes from our measured data.